Okay, so welcome back. The topic this week is slightly different from what we've been doing before, and it deals with statistical analysis. And this is something which can sometimes be a little bit delicate in the sense that the way we have restructured the bachelor programs in many countries, actually, we've left out a proper course in statistics. So many of you may not have taken a course in statistics. You've seen some of the concepts here and there, but that means that you don't get a coherent exposure to some basic statistical concepts. I don't know if I will be able to, cure that problem, but I will step you through some of the basic elements. So the overarching message is simply that when you run a statistical calculation, a stochastic calculation, like a Monte Carlo calculation, if you don't provide an estimate of your standard deviation, your error, people will just send back your results and say, please come back with an estimate of the error in your calculation. So the reason for this is that we don't have the luxury of being able to calculate exactly the integrals. That means that the energy which you get, which is our mean value, the expectation value, is going to be something which we in statistics call the sample mean. So you have a sample of Monte Carlo cycles, and what you would like to have is to have an infinity of such samples, because then you should approach the exact result. There is something which is called Bernoulli's law of large numbers. But the problem is that this kind of luxury is something which we do not have. And we are always confined to run calculations with a given number of samples. And that means that we calculate the sample mean, which may not be the exact mean, but hopefully it's getting closer and closer. But since we do that, we need also to evaluate the variance, which is the spread in the mean value squared. And when you take the square root of that one, you have what's called the standard deviation. And I guess you've seen these concepts in different courses. And for some of you who've taken a course in statistics, this is something which is normally elaborated in quite some detail. But we are going to look at some techniques which are called resampling techniques. And there are some popular resampling methods which I wanted to discuss. And one is widely used, and it's called the bootstrap method. And then we have another one which is more suitable for the data which we have, which is called the blocking method. Now, one of the things which I wanted to do is to take the top-down view first, so that you see the programming elements you need. And when you have these programming elements, you could actually just take this data which we have, or this example, and then run one of the codes for resampling. So the top-down approach is that now you are going to produce an output file with the mean values for the Monte Carlo cycles which you're doing, and you can think of these as an observation. So suppose you do 100,000 Monte Carlo cycles. You may not write out all 100,000, but you could write out, let's say, every 100 sample, you write out the mean value. So that becomes an observation. Now, one thing which we have to struggle with when we run these Monte Carlo calculations is that the stochastic variables are not independent. They are hopefully identically distributed, so there could be a Gaussian distribution behind the stochastic variables. But in general, they are not independent because they are generated by a random number generator, which is based on a linear algorithm. So there is a dependence between the random numbers. Furthermore, there are correlations in the data sets themselves, because you have an interaction between the particles, which also creates some type of correlations. So the stochastic variables we have are not fully independent, and they are ideally they should be identical and identically distributed, but we may not have these conditions in the analysis of the data. So there are resampling methods like this blocking method, which tries to take into account these things. And we are going to go step by step through some of the statistical elements so that you get the background. But the top-down approach is that you take your Monte Carlo code, you write to file the expectation values as a function of number of Monte Carlo cycles. And then when you have that file, you can use the software, which we have in the lecture notes here, and do the statistical analysis and get the final expression for the standard deviation. So the standard deviation results from an integral, which in principle is something you would like to, I would say, evaluate as quickly as possible, but sometimes it can be trickier to evaluate. So there are ways to actually calculate, because you will have correlations in the data, which means that from a statistics point of view, you need to calculate the covariance matrix or the covariance. I'm not sure if you're fully familiar with that, but I'm going to define the covariance. And the covariance, if the stochastic events are independent, then the covariance is exactly equal to 0. Unfortunately, we will have correlations between the stochastic events, which means that our covariance matrix is non-zero. And that introduces some additional things which we need to deal with when we calculate the standard deviation. So I'm going to go through some of these elements. Now, the covariance matrix implies a double loop. So if you are running your Monte Carlo calculation and you do 1 billion samples and you would like to calculate the covariance, it means that you would have 1 billion squared calculations, and you don't want to do that. So these methods, these resampling techniques, are ways to obtain an estimate on the standard deviation, which we can present when we discuss our results. Because as I said, the overarching message is that you are calculating a stochastical integral, an integral in a stochastical way. You're getting a mean value, and then you have to present what is the error in your statistical analysis. And that is the standard deviation. So it sounds like an incredibly cumbersome approach to get a tiny number which reflects the error. But this is something which we have to provide because we have the tools to do the statistical analysis. So I wanted first to give you this kind of top-down view and go through the code and show you which elements we need to set up and what kind of strategies you should land in your final project here. So the bootstrap method, I have some videos. There's also this is actually a very interesting thing which happened, because sometimes when we teach this course, some people come up with ideas which end up with scientific articles. So Marius, he was actually following these lectures, and he went into the mathematics of this blocking method, and he was not very happy with it. So he had a very strong background. He had a bachelor degree in statistics. And then he actually improved this method, and that resulted in a scientific paper based on his master thesis. So he was just looking at my derivation, which was based on a paper by Flygberg and Petersen from two Danish researchers from back from the 80s. And he was not satisfied with the mathematical proof. That was pretty neat. So what I want to do now is to take this top-down approach and show you what you need to do. So think of the statistical analysis not as something which you have in your production run. So your production run is your Monte Carlo code written in a as efficient way as possible. And then you spit out the mean values and the expectation value of the energy squared. And then you use this in a post-analysis. That's why we will typically write the results to file here. So the code here is this code which we have been looking at throughout the semester. So we have these two electrons interacting with a Coulomb interaction. These are two electrons in a quantum dot system where we have a harmonic oscillator potential. The wave function is given by a harmonic oscillator times this correlation part or Jastrow factor. And then we have a local energy which can then be derived analytically. We have the derivative of the wave function with respect to the variational parameters. In this case, we have two parameters, one in the harmonic oscillator part, which is the alpha piece, and then we have one in the Jastrow factor, which is this beta parameter. These are the parameters. And then we calculate the quantum force. There is a function which sets up the derivative of the energy with respect to the variational parameters. And that is this equation with free integrals, which we discussed last week and the week before. So this runs through a calculation of the derivatives. And there's also a function which sets up the energy. And then when you look at this function here, what I'm doing is that if I have this printout true, I print out now the expectation value of the energy to find. So here I have two particles. And in the first case, I now run the calculation to find the optimal values of the parameters alpha and beta. And that gives me a calculation here, which gives me a minimum. And I'm implementing Broyden et al.'s method, as we discussed last week. It takes an initial value for the parameters alpha and beta. And in this case, I only have 10,000 Monte Carlo cycles. So this is what we call the cheap calculation, to find the minimum. Then, when I found the minimum, then I start the production calculation. And in this case, and you will see later why we do this in powers of 2, in base 2, because this is something which is tailored to this blocking method. So here I'm running, I could run millions and billions of Monte Carlo samples, and then I spit everything out to file. And the write out to file here is then something which I will later use in an evaluation with resampling techniques, which we have to discuss now. So the calculation which you see here is me finding, after I've done the calculation, the optimization. It took, with the Broyden et al.'s method, it took 4 iterations. And then I run my big Monte Carlo machinery. And you see now that my final energy is pretty close for this frequency, which is equal to 1. It is pretty close equal to 3. And the exact value is actually 3.00. So this is my Monte Carlo calculation, the final estimation, the production run, as we often call it, with 2 to the 19th Monte Carlo samples. And we're getting pretty close. Now, when you run it for the non-interacting case for this bosonic system, you will basically be spot on the exact value. But then what we have next is a resampling analysis. So I wrote to file the expectation value of the energies. And now I'm going to use either the bootstrap method or the blocking method. And I'm going to go through the details behind these methods so that you understand what they're doing. If you want to do something quickly, you could take these functions and do the post-analysis. So the resampling technique is something which you do on top of your production data. So you have a big, heavy-duty production calculation which you run, that produces an output, and then you do the statistical analysis on top of that. And in this specific case, and we are coming back to what this means, you will see now that it produces a mean value of all the results which I put out, which is as close to 3 as you can get. And it has a standard deviation of 10 to the minus 5. This is a standard deviation. Then I have the blocking code, which you should feel free to use, and which is a code which is provided in Mario's article. And in this case, it gives a slightly different standard deviation. And I will try to explain you why these methods give us slightly different standard deviation. But what you see is that the mean value is the same, but the standard deviation can vary depending a little bit on which resampling technique you do. So I will try to explain to you why you can get different results. So we will say something about this next week as well. But the important thing now is that when you present your results, after all this hard labor, at the end, what you present is just this number and this number. So it sounds a little bit disappointing when we do all this labor, that these are actually only two things which we present. This is when you run calculations with Monte Carlo methods, which are stochastic methods, we have to have the mean value plus minus the standard deviation. And these methods are meant to provide you with an estimate of the standard deviation, which is as reliable as it can be. Okay? So this is the top-down view. Any questions about that? Does it sound okay? What we need to do? So feel free to use these codes, and this is something which we have done every year. You don't need to write your own bootstrap method. You don't need to write your own blocking method. The bootstrap method is actually included in, I think it's included in NumPy in the statistics package. So you can actually use that one there. But I'm going to explain to you what these methods are doing so that you have a understanding of it. And for those of you who have taken a course in machine learning, you have already encountered methods like the bootstrap method, which is a popular resampling method together with the cross-validation, which is another resampling technique. So in statistical analysis, there are many of these methods. And then the question is, which one should we use? Okay. So I hope the overarching message is clear. So in your code, the thing you need to do after you found the minimum in terms of the variational parameters, like we do here, then you launch your big Monte Carlo calculation. And then you can decide whether you spit out the expectation value of the energy each 100 cycles, each 1,000 cycles, or whether you write out every one. But clearly, if you do 1 billion cycles, you will have a file with 1 billion data points. And if you're doing double precision, this is 8 bytes per number. So that means 1 billion times 8. So that would be a huge file. Okay, so what I wanted to say a little bit about is these resampling methods. And the thing is that I just wanted to give you a quick understanding of why we do resampling. So your calculations, they are to be viewed as computational experiments. So that means that when you run a calculation on your laptop, I mean, your laptop can actually produce slightly different results every time you run it. Hopefully it doesn't do that, but there could be heating problems, for instance, which would give slightly different results, especially when you run a stochastic calculation. The results then should be analyzed with the same statistical tools as when you analyze experimental data. And for those of you doing experiments or analyzing CERN data, this is something which is, or doing subnuclear physics experiments, this is something which you have to deal with. And as in all experiments, you're looking for expectation values and an estimate on how accurate they are. So we want to estimate the errors. So in many numerical experiments, typically you have statistical errors, and we can handle those because we have tools to do that. The things which are difficult to deal with are systematic errors. So one systematic error we have in these calculations is obviously the Hamiltonian which we are applying. So in the case of bosons, the Hamiltonian we made up is a model. That may not reflect physical reality. So that will be something which leads to a systematic error. So systematic errors are much, much more difficult to deal with. And we will just put them under the carpet. And we are just going to look at the statistical errors. So what I want to do now, just to switch over to the whiteboard, and we are going to look at some of the statistical errors which we can have and the different methods like bootstrap. There's another method which is very popular, which is called jackknife. And then we're going to look at the blocking method. But I need to give you, since not all of you have taken a coherent course in statistics, I'm going to bring in some of the basic elements so that we are basically on the same page, all of us. if that is okay. Okay. So if you've seen these things before, I hope you don't get offended if I repeat them. So let's just switch over to the whiteboard. Let's do that. So if we look at the bootstrap method, which is one of the standard methods, so we are going to roughly go through two methods, and we will also mention the jackknife method, which is also very popular in this statistical analysis, resampling analysis. So if we now look at this resampling or statistical analysis, I'm going to put this as a slash. Sometimes we use this as synonym. And we are going to focus on two methods. One is called the bootstrap, and this is extremely simple to set up. And we may also say something about the jackknife. And then we have the blocking method. And these are the two resampling techniques which we are essentially going to look at. So this, if you look at this bootstrap method, the standard bootstrap, that assumes that we have what in statistics is called independent and identically distributed stochastic variables. So the bootstrap method assumes that our events, that the stochastic variables we deal with if we now have a stochastic variable xi, that they are what we call ID, and you probably met this acronym in statistics. So one is that they are independent, and I will try to explain to you what it means that they are independent. And then they are identically, and D stands for distributed. So they are independent and identically distributed. So I will try to explain to you what that means. So the estimators are typically, so estimators is one of these words which we are going to encounter and which you actually have been computing throughout the semesters. So the estimators, the quantities we want to evaluate, in our case, they are typically the mean value, which we have been evaluating till now, or what's normally called the sample mean. So let's just slowly switch over to the next slide, if that is okay. So we are going to look at the mean value. And in order to be precise, we should say that this is the sample mean. And I will come back to what that means. And the sample variance. And from the sample variance, that's the quantity which we use then to evaluate the standard deviation. So let me set up some of these basic definitions here. So if you look at the expectation value of the energy for a given variable x, suppose now we just replace the energy with this x. So this is the way you would typically encounter the statistics books. And then we have this more sloppy physicist way of indicating the variance. And this is given by, if you now have a continuous probability, so we have an integral where x is now defined for a specific domain. We have a probability P of x times x of d of x. So this is normally called the probability distribution function, PDF. Or you would have the discrete variant. and then I is element of a specific set of stochastic events. And this is now given by some x of I, and then we have some probability. And let's now just write it with an upper X here, with X and little x of I. So this X, which you have here, this defines the set of events for the discrete case. So this I, this could be some x0, x1, up to some observation xn minus 1. Okay? So this is the definition of the expectation value in case we have either a continuous or a discrete probability distribution. So discrete means simply that we have discrete stochastic events. So like you tossing, let's say a dice, you know that you have 6 possibilities. So the thing is that this quantity which we have here is normally unknown to us. So this is unknown. If we have it, then we are lucky because then we can eventually calculate the integral either analytically or numerically. But in general, we don't have the probability distribution. So since we don't have this P of X, not knowing P of X, so this probability P of X of I here, that means that we don't have, if we don't have it, we need to evaluate the sample mean. We evaluate the sample mean. And the sample mean is something which I will label with a mu here. And that is simply 1 over n. And then I have a sum over all the possible samples which we have up to some n minus 1. And then I have an x of I. And this is in general different from the true expectation value. So suppose you have the exact probability distribution, then you may not get a mean value which is equal to the exact one. So in this case, what we are typically inferring is what is called the Bernoulli's law of large numbers. So in the limit where this n goes to infinity, then we should in principle be able to approach the exact value. So what you see now in this specific case is that the probability which we had in the previous expression, if you now compare this with the exact expression of I equals 0 to n minus 1, and then we have a probability for x of I times x of I, you see now that when you compare these two expressions, what we are doing now is that we are giving the same probability to all the events. So that means that what we have done is to replace our lack of knowledge of P of X with a uniform distribution where all events are equally probable. Another thing which we should keep in mind is that the probability is always normalized. We are assuming now that this is normalized to 1. Alternatively, if we have a discrete probability distribution, then we have the sum over all the events of x of I, and that's also equal to 1. Then we have another important quantity, which is the variance. And we know that when we do Monte Carlo calculations with a Hamiltonian or quantum mechanical variational Monte Carlo calculation, then we know that if we have the exact wave function, then the variance is equal to 0. So this is for us one way of knowing at least one of the quantities we want to evaluate. So the variance, if I can, is it okay if I shift? Yeah, let's just wait a little bit so you get time to write down things. I know for some of you, these are familiar things, but since the audience is pretty heterogeneous when it comes to statistic background, I'm just taking the liberty here of repeating things which may be obvious for some of you. Hope you can forgive me for that. Okay. So the variance itself is a quantity which I will label like the variance of X. And this quantity is then defined formally if we now have a continuous distribution. So we have this P of X, and then I have X minus the expectation value of X squared of D of X. Alternatively, if I have a discrete probability distribution, then I have I elements in D, and then I'm summing over P of X of I, and then I have my X of I minus the mean value squared. And this is a quantity which we typically write out. So this specific quantity becomes equal if we now write it down. So if we take this number and just write it out generally, this is the same as the expectation value of X squared minus the expectation value or the mean value squared. And it's pretty straightforward to see that when you calculate these expressions. And that means that when we, in our code, what we need obviously, we need this quantity and that quantity. And with these two quantities, we can then evaluate the variance. So the variance is a quantity which is always larger or equal than 0. It can never be negative. If you get a negative variance, there's something wrong. And for our case, if we have the exact wave function, and you have seen that when you run the calculations, that the variance is exactly equal to 0 when you have the exact wave function and you get the exact energy. So this is if you don't know the energy, what kind of energy value you should get, and somebody gives you 2 to 3 different trial wave functions, then when you run the calculations with these different trial wave functions, you would pick the one which gives the lowest energy and the lowest variance. So the standard deviation is then, this is the quantity we typically add, is then the square root, or STD, as you will see. That is simply the square root of the variance. Now, what we are going to do is to calculate the sample variance. This is the quantity we will look at. And the sample variance is, in a way, the one we have to live with. The same as we have the sample mean value, which is the other quantity we have to live with. Okay, so the quantity which we will end up evaluating is the sample variance. And I'm going to simply label that one with a sigma squared. And I'm going to put an X because now I'm looking at the variable X. In our case, X is the energy. And this is now going to be given by 1 over n again. And then we sum over all the events which we have up to n minus 1. And then I have my X of I minus, and then I have my mean value, mu of X. So remember now that my sample mean, so this is squared. So this is my sample mean. And this is going to be equal to 1 over n. When I now do the calculations, this is exactly what we end up doing, minus mu of X squared. So the quantity which we need in addition is that expectation value of xi squared. Now, this quantity is not the same as the variance, the true variance of X. Okay. So one thing I wanted now, when we've been saying these things, suppose I have 2 stochastic variables, x1 and x2. Then the question is, what does it mean does it mean that x of I is, what is the consequence here? That these stochastic variables, so when I say now these variables x, I'm assuming that these are stochastic variables. The stochastic variable is obviously generated by some random type of events. A non-stochastic variable would be you running an experiment where you fix, for instance, the velocity of a particle. Because then that variable is not stochastic because you have fixed the energy and the velocity of a given object. So if you run an experiment at CERN, for instance, and you have protons with a given velocity and your beam does not have a big spread in velocities, then you would say that my velocity of the proton beam is precisely set to that velocity. And then you would not consider that as a stochastic variable, unless your beam has a spread in velocities, but then your velocity would then be concentrated around a specific mean value. And you would typically not consider that as a stochastic variable. Okay, so if we now ask ourselves what this means, let's take a look at a probability of two particles. So we have x1 and x2 as stochastic variables. And in that case, we have a probability of x1 and x2. And the question is, what does this look like if we have independent stochastic variables and identically distributed? So the identical distribution means that this P of x1, and if they are independent of each other, is now given by distribution P of x1, which is the same for the two variables, x1 and x3. If they are not independent and identically distributed, then we need to have an expression which looks like this, where we cannot specify it in terms of two probabilities. So as an example here, you could have this as a Gaussian distribution or a normal distribution. So as an example, so this could be the normal distribution. So that means that this P of x of I is then proportional to E of minus x of I squared divided by 2 times sigma squared. So where the sigma squared is the variance for this specific event. Now, this has quite some important consequences for us, because there is another quantity which measures the degree of correlations between two stochastic variables, and that's called the covariance. So meet the covariance, that is our next quantity. So if I want to calculate the covariance of xi, and xj, this is formally written as an integral over dxi, and then I have a dxj. There is a probability distribution of p of x and xj multiplied. So let's just mark this with red, so that this is not the variable x, but this is just a multiplication sign. And then I have my x of I minus, and then I have the expectation value, which I'm now writing in a more compact way. So this is the mean of xi. So these are just two stochastic variables, minus xj, like that. That is the covariance. Now, if these are independent and identically distributed, if xi, xj are IID, What happens then is that this P of xi of xj is then equal to the same probabilities of xi P of xj. And what happens in addition is that x of I, the average value, is equal to x of j. And I'm just going to put this one to x like this. Okay. And you can see that because if these are independent of each other, they have the same mean value. So if you have a normal distribution which describes two stochastic variables, then they have the same mean value. Okay. So if I do that, then this expression changes to the following. So what I get is now an integral over dxi. I have an integral over dxj. I have the same probability P of x here, and this is the same, so these are bars, xj's, and this is multiplied with xi minus x, multiplied with xj minus x. And these are obviously integrals which we can separate. And then I have xi minus x of P of xi multiplied with dxj of xj minus x of P of xj here. And here you get a famous number, which, if you look at the expression, what would you expect? And let me just remind you of two small things here. So if I look at the integrals which you get, so you have a dxi of xi minus x multiplied with P of xi. If you look at that integral, that is going to be an integral over dx xi P of xi minus. And now this is a constant. And then I have P tilde xi dxi. This is normalized to 1. So what would we get then for each of these integrals separately? You see what we get? There's a famous number. It's actually the roundest number you can think of. So this quantity, let me give you another hint. This quantity is actually the mean value. So what is your guess, guys? Before we take a break. Yeah, so this, because these two numbers, each one of these are independent variables. So we have separated out the calculation here. And that means that we have 1 over xi, 1 over xj. And you see now this is x, the mean value. This is just 1. So it's the mean value minus the mean value. And you would get exactly the same result for this one. So what we say then is that if we have independent variables, they are not correlated. So if the covariance is different from, so the covariance is a measure of the correlations between your data points. So one problem which we will have in the Monte Carlo calculations is that the stochastic numbers which we generate, they are not exactly independent of each other because we have a deterministic algorithm. So if you were given a true random number generator, then we should have a covariance which is equal to 0. But there is a deterministic algorithm which you use to generate random numbers. So the random number generators is a generator which you are going to use zillions of times. And you want it to be fast. You could look up a table of randomly generated numbers, but that would take much more time. So there is always a compromise in the calculations which we are running. So there's actually one source of a small error in the calculations is that the random numbers you generate with what we call a pseudo-random number generator, they are not exactly independent of each other. And that means that you will have some type of correlations in the random numbers themselves. So that means that we are not producing exactly independent and identically distributed variables, which means that we will have a small impurity in the covariance, which measures the degree of correlations between stochastic variables. So these methods, like the blocking method, is a way to actually evaluate the covariance for us. So if you have variables which are not independent, then this number is not zero. So the larger the number, the stronger the correlations. So some of you are probably familiar with the correlation matrix and the covariance in machine learning analysis. So if you take an analysis of housing prices, you would find, if you calculate the covariance and the correlation matrix, which is just a scaled covariance matrix, you would find that there are strong correlations between the price of the house and the number of rooms you have, the size of the house and the number of rooms, but the correlation between the price and the color of the house is probably very small, because most people would typically repaint the house when they buy it, because it's seldom that you're happy with the color of the people you bought the house from. So most likely the price is not strongly correlated with that quantity. So to calculate the correlation matrix and the covariance matrix, or the covariance, is actually a very important aspect of the analysis which is coming. So everything here sounds like not too exciting topic. It sounds actually pretty boring, but there are some things which we need to take care of, because at the end we are running a stochastic calculation and we have to provide an estimate of the error. So it's a long journey to get there, but for us, when it comes to the project, you should feel free to use those programs which I have listed, and then just do the post-analysis. So now I'm just going to guide you through the statistical derivation of these methods. I see that we are getting close to the hour. Actually, went a little bit over time. So let's take a small break. So the topic which we are going to look at now more in detail is to link some of these basic things with the bootstrap method, the blocking method, but we need also to remind ourselves a little bit about the central limit theorem. That is going to be essential, in particular, since our covariance is not going to be equal to zero. So that's a problem which we will typically have to live with and find a way to cope with. So let's now take a look at one of these methods first, because the bootstrap method, which is the first one we are going to look at, is extremely simple to implement. And it's a method which is directly linked if we have independent and identically distributed variables. It's directly linked with the central limit theorem, which we are going to say something about as well. So the method itself to set up the recipe is very straightforward. So let's now assume that we have an original sample. And let's call this for upper letter X. And then we have an X1, X2. So these are the events or the stochastic variables which we're looking at. And what we assume now is that we can produce new events, new sets of events, or new samples. So this is the original sample, by simply reshuffling the data which we have in the original samples. So we assume we can produce new samples. And let's call these for X star, like that, and produce new estimates. So what we are calculating now are actually the mean values, the sample mean, and the sample variance. New estimates for mu and sigma squared. Now, the way you could think of this now is simply to rerun the experiment. So suppose now that you have an experiment which gives you this set of sample, then you could simply rerun the experiment and get a new set of samples. However, if you are at CERN, to give you an example, since we have people doing experiments at CERN, or you're doing an experiment in nuclear physics, an experiment at CERN can run for half a year. A nuclear physics experiment has a typical duration of a week, could be some few days, but normally it's a week of constant beam hours. So if you run an experiment at CERN, and this is your data set, and the experiment took half a year, and you look at, for instance, at the electricity bill, there is no way they will give you another half a year beam time because you got some faulty statistics, unless you can claim that this is as close as it can be to a Nobel Prize. So unless you have such big claims, there is no way you can produce new data. This is the typical situation which we end up with. So if you're running a medical survey and you're studying correlations between, let's say, diabetes, heart attacks, strokes, and so on, you may be surveying a group of people for, there was a survey in the UK now, which has lasted 30 years. And the data you have, so this surveyed something like 500,000 people. And the data you have then are the data you have. So that means that when you do a statistical sampling of the data, you do a resampling and you want to assess properly these variables, then what you can do then is actually to use the same data set and reshuffle your numbers. So what you would like to do now, ideally, you could rerun the experiments, so you could produce many new experiments. So I'm just gonna set up the variables. So you could think of having the following variables. You could have a new sample. So this would be experiment 1, which comes on top of the one you had. You produce this one, then you produce a new set of, I put a number 2 here, of n, and this could go all the way up to some n here, where we have a b. So this is the set of experiments which we are producing. So you have experiments from 1 to b. And what you would like then, so each of these numbers could now be the mean value. So if we now put an I here, that would be given by a sum over 1 over n. And then I have a sum over j equal 1 up to n. And then I have my xj for this specific experiment, which is experiment I. Okay. So the final value which you then would evaluate would obviously be a theta b after b experiments. So the final mean value in our case then would be one which collects all these experiments. And hopefully that one brings us closer and closer to the exact value. So ideally, every one here is a new experiment. That's the ideal. But as I said, if you are running an experiment at CERN, it's very unlikely that you will have a new experiment. So let's look at the final value which you would get then. So what you would like to estimate at the end would be a theta of b. And this is a mean value. I just put a bar on top of it. And that is now the sum over all these mean values which we have. So this would have a sum from I equal 1 up to B. And this is a theta of n. So we have n experiments in each one of them. And this is experiment I. Okay? And then the variance of this quantity would simply be the variance of this quantity, the average value here. This is our estimator for the, and then we would have a B. And often there is a bias, so you would find a -1 here. But if B is large, we can skip that. And we have I equal 1 up to B. And then I have my theta n of I minus, and then my mean value of B here. And that is squared. So these are the quantities we would like to evaluate. Now, the bootstrap method is actually extremely simple. So we are just going to state the algorithm now, and then we're going to trace back and look at proofs for it. But before we do that, we need to say something about the central limit theorem. So the bootstrap algorithm. So let's now look at the original data. So we have the data we feed in. Could now be something very exciting, like 1, 2, 3, 4, 5. So suppose we have these data points. These are our stochastic variables. They don't look like stochastic variables. Then we produce a new data set. We produce an X prime by shuffling randomly these numbers with replacement. And if we get some time next week, I'm going to go through the proof that this actually gives the correct values for the variance and for the mean value. But you could now reshuffle it randomly so that your X with replacement could now look like this. Could be a 2, 3. But then, since you're doing replacement, it means that you can hit the same variable more than once. So you could have 3, and then you could have 5 here, and 1. So this will be your new data set. So if you look back at what we had on the previous slide, we would then produce many such data sets. And each of them can be treated as an independent, almost independent data set. So this is what you might call a poor scientist's approach to the problem, because you cannot repeat the experiments. So the data you have are the data you have. And that calculation, which I showed you in the previous lecture, was with the bootstrap method, is actually based on this technique here. Now, later we are going to see in the slides how we can actually demonstrate the central limit theorem with the bootstrap method, a numerical demonstration of the central limit theorem. But the basic idea here is that you reshuffle this many, many times. So suppose you have 10,000 data points. And in the example which we are going to look in the Jupyter notebook, I could take a normal distribution and generate 10,000 points with that. I can then redo this 10,000 times by generating new data. That's fully possible. Or I could take the original 10,000 data and reshuffle the numbers 10,000 times. Because sometimes to generate the data with a given distribution can take a lot of time. And reshuffling them, like we do here, is something which is much, much easier. So the typical way you would set up the bootstrap algorithm is simply now by setting up the number of parameters, the number of reshufflings B. So this could be, if you have 10,000 data points, you could say, I do this 100 times, or you do it 1,000 times. So that means that every time you do this, you generate a new data set. So mathematically, you can actually show that this approaches the true mean value and the true variance. So when Efron introduced this method the first time, it was more in this kind of intuitive ad hoc way. But then later people came up with a proof that this actually approaches the correct values. And if we get some time next week, we will go through that proof. Okay, so this is the bootstrap method. In order to get some feeling with it, we are going to dive into the central limit theorem and just remind ourselves about that one. So let's use the rest of the lecture on that. And then next week, we will try to wrap up the discussions of the statistical resampling methods. So we will need roughly 2 double lectures for that. But I think it's important to understand a little bit of what these methods are doing. So from the project point of view, you can use, and this is something we have done every year, you don't need to write your own bootstrap algorithm. You don't need to write your own blocking method. Just use those programs which I provided in the lecture notes for this week. So if we now look at the central limit theorem, so suppose now we have a set of experiments. So we have M experiments. And each of these they have a mean value. So I'm going to define an experiment. So this is experiment I in this set of M experiments. And each experiment could then have a given number of samples. And this is now given by some sum over j equals 1 up to n. And then I have an xj. And this is experiment I. We're also going to assume that all these are identically distributed and independent variable. Okay, so I'm going to simplify the notation now, since these are IIDs. Simplify. So I'm going to let this xi bar, I'm simply going to replace that with an x of I like this. And what is important is that there is the same probability distribution behind each of these mean values. So this is the mean value for experiment I. Mean of experiment I. And then I have a total set of M experiments. And we are using the same probability distribution because we are assuming that all the stochastic events are given by the same distribution. Okay? So you could think of having the uniform distribution. It could be the Poisson distribution, any known distribution here. So this means that we can set up the total mean value. So the total mean, and we just call this Z, is going to be the mean values of x1 plus x2 plus plus. And then we have our xi here, plus plus. And the final one is xm, the final experiment, divided by m. So the thing which we are going to, if you now look at this expression here is nothing but the one which we wrote previously in terms of when we discussed the bootstrap method. So if you go back a little bit, this Z here would then simply be the same thing which we put up here. So we have a set of experiments and they all contain n observations, and the final or the expectation value for a given experiment is given by this one. And then the total one is now given by the total number of experiments we do, often called batches in the literature. And the only difference is that I've replaced B with an N in the expression which you see here. So the question is, what is the distribution? So we assume now that you know the distribution for the individual ones. What is the distribution, which I call TZ? And I'm going to put a bar on it. So we know the individual ones. So we know these small guys, P of X of I, they are known. And all of these have the same distribution. So that could be, let's say, a Poisson distribution, a student T distribution, a uniform one, an exponential, a Gaussian, or whatever. And then the question we're asking is, what is the distribution for the final one? When we now look at all these measurements put together. And it shouldn't come as a surprise that if these variables are independent and identically distributed, that the final distribution is going to be a Gaussian. This is a central limit theorem. But beware now that this assumes that all these small guys here, these ones, are independent and identically distributed. That's a fundamental assumption, because else you cannot derive the central limit theorem. So I always tend to joke about this kind of trend, which we had in many countries in the world, with forcing a Gaussian distribution for the distribution of grades. And you know that for the big numbers, it looks like a kind of Gaussian. But if you break it down into small classes with 10 to 15 students, that may not be distributed according to a Gaussian. I actually had a teacher in high school who enforced that. So only one, because he had found that only one could get the top grade. And even if you had everything correct, you would never get the top grade because there was only one who, according to the Gaussian distribution. I will never distribute grades according to a Gaussian. I never do it. That's an offense, actually. Okay, so let's now see a way we can model this one. And the typical way you would do that is to set up this one by integrating all over the other ones and putting a constraint. So what I would do then is to have an integral over x1, which is member of the same set of domain. So you have a dx1. This is the same as that one I would have for x2. So there would be an x2 here. And these distributions are the same. So they would, same domain. And this continues all the way up to the final one of x of m. And these are the distribution of the mean values now. Remember that, eh? The x's here are the mean values because I introduced a shorthand for that. So this would be a dxm, and then there is a p of xm. But now I have a constraint, and that is a constraint through a delta function. And that is given by z minus x1 plus x2 up to xm divided by m. Now, what I can do now is to, I'm going to do some manipulations in order to show you how we derive the central limit theorem. That's okay if I change? Okay, so the delta C, we are just going to rewrite that in terms of the standard expression for the delta function. So that has an x1 plus x2 plus xm divided by m here. And we know that we can rewrite that one in terms of an exponential with integration from minus infinity to plus infinity. And this has a variable of, so this is the exponential. And then I have an iq, and then I have z minus, and then x1 plus x2 up to xm divided by m, like this. Now, the thing is that these variables, these x1s, x2, etc., they are the same. So if I look at this p of x, d of x, which is given by x now, and we have an I, I'm simply going to replace that one with a mu here. Because since these are the same probability distributions for all these variables, they have to give the same mean value, which I'd simply call for mu here. So in this expression, what I'm going to do now, I'm going to insert just one in this expression for p z. I'm just going to insert one, and I'm going to insert one as e to the I of, so this is just a calculation trick, minus I of mu times q. And I have defined this mu to simply be given by this quantity here. So I'm just going to do a small rewrite of that integral over all the x's. And that means that I can rewrite that final integral in the following way. So let's just wait a little bit so everybody can write down the expressions. I always have, I always make a copy of these notes so you can fetch them in the so-called handwritten notes folder. So what I get then is that this P of Z, this probability we are searching, can now be written out in terms of an integral which can be solved. So I have a sum, an integral from minus infinity to plus infinity. There's a dq e of iq, and then I have z minus mu, because I had mu m times, and then I divide it by m, so that simplifies. And this is then multiplied with all these integrals because they are the same, since the probability is exactly the same. So I have a d of x of p of x, and then I have the exponential, and this exponential has I of q of mu minus x divided by m, and this is to the power of m. And then what we also need to remember now when we are looking at these expressions is that these x's are normalized. So we know these probabilities. So the p of x is known. So we start with some data which are distributed according to a given probability. And what we're also going to do now is to take a look at one of these terms. So let's take a look at this term here. So let's just break it down a little bit and just look at this term, this integral. So we now look at the integral over x, d of x, e of x, of e of I q of mu minus x divided by m. So let's just take a look at only that part. And then this is going to be exponentiated with m. So this is something where what we can do now is simply to perform the Taylor expansion of the exponential. So we know that if we Taylor expand this one, then that's just going to be equal to x element d, and then there's a p of x, there's a d of x, and then I simply Taylor expand the exponential. So I have 1 plus I of q of mu minus x divided by m. So mu is just a constant, minus, and then I have q squared, and q is not involved in that integral. And then I have a mu minus x squared, and this is, no, not x squared, sorry. I have to be a little bit careful here. Minus mu, this is x, mu minus x squared, and this is now 2 over m squared, and this continues plus 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 to higher order terms. So if you look at these terms now, when you look at the integrals, can you recognize what the first three terms will look like? So let me just give you one hint. If you look at this first term, this is multiplied with that one, and you recognize this as this one, right? So the first term here, when we integrate it out, it's just going to give us 1. But what about the second term? So remember now, this is the mean value, mu. So let me just bring it back here. We have defined that one to be this quantity. And here I have minus x. Q is just a number which doesn't affect the integration. And the same with the complex number I. So what would you expect from the second term? If you take into account this result, which we have put in here. Any good suggestions? Yeah. Yeah. Yeah, U is this one. This gives you the mean value. This is just a constant. And this is a constant multiplied with that one, which is 1. So it becomes mu minus mu. So this is going to be 0 again. What about the third term? Can you recognize that as a specific expression? The variance, exactly. So if I write this out, what I get now is 1, and then plus 0, and then I get minus q squared, and then I have a sigma squared divided by 2m squared, and then plus plus. So that is my Taylor. So it means I get higher moments, and some of these higher moments are actually going to be 0. So then I'm going to bake this one. What I'm going to do now, I will simply stop. So you can actually rewrite this one in terms of a Gaussian. So I will make an approximation, because you will see that all the odd powers are going to be 0. And then we are going to get higher powers of even powers. And then if we neglect those and just keep the first terms, then we can show that the final expression, when I plug this term back into here, so I have to perform that integral. But now I made an approximation where I include only the variance. So I have to perform this. I have this to the power of m here. And then I have to perform this integral. So I'm not going to give you all the details there, but I want to give you the final result. So the final integral is going to be equal. So in the limit, so I'm going to skip many of the calculational details. In the limit where n goes to infinity, then this distribution P of z is going to be equal to 1 divided by 2 pi sigma squared divided by n. And this is the exponential of minus, and then I have z minus mu squared divided by 2 times sigma squared divided by n. And that's a Gaussian. So that's a Gaussian with mean value mu and variance sigma squared divided by m, which means that the standard deviation is going to be equal to the famous result, which you have seen many times, sigma divided over square root of m. And this sigma, which you have, this sigma squared, is actually the variance of a single experiment. So this is something which is true in the case where your observables or your stochastic variables are actually given by a independent and identically distributed set of variables. So the thing which we also need to remember now, and just keep that in mind, this sigma squared, so let me just put that up and go back again. This sigma squared is just the variance of a single experiment. So where I have x minus mu squared of d of x. So this is what we call the single experiment variance. And this is the central limit theorem. So what we have is a set of variables which are given by an independent and identically distributed set of stochastic variables. Then when we run this in terms of many types of experiments, then the final distribution, if our starting point is given by independent and identically distributed events, the final distribution is going to be a Gaussian with the same mean value, but with a standard deviation, which is given by the original one divided by the square root of the number of experiments which we make. So this is a very important result. Now, what we are going to do afterwards is actually to look at how the bootstrap method, if that one is able to reproduce the central limit theorem. So we're going to run some numerical experiments where we simply demonstrate that the bootstrap method gives us this final result. So in the numerical experiment, which you will find in the Jupyter notebook, we start with a Gaussian distribution with a given mean value and a given standard deviation. And then we simply redo this starting with 10,000 points. We redo it 10,000 times. So if we do it 10,000 times, it means that our standard deviation then, if it follows the central limit theorem, then the standard deviation should actually be given by the original one divided by the square root of 10,000, which is 100. And so let's just try to see that, but I see that time is running a little bit out. So let's see if we get time to do that. So I'm going to switch back to the Jupyter notebook. So in the slides here, you will find many of these basic arguments as we discussed in the previous lectures and also this lecture. And we discussed stochastic statistics, independent variables, etc. So everything we put on the whiteboard are things which you will also find in the slides here. And then, so if we now go back to the, so a little bit down here, this is basically the central limit theorem. But there is a code here, not here. Did I forget to put it in here today? No, we should have it here. So in this specific code, I'm implementing the bootstrap method. And the way you do the reshuffling, there is a nice function in Python for the random library, where you do random int, and this is your data set, and then you just do it n times. So this reshuffles your data and does it with replacement. So this is the way I'm doing it. So I'm starting with a Gaussian distribution. This is my original data set. where I now have a mean value, which is 100, and a standard deviation, which is 15. And I do 10,000 data points. So these are my variables. And then I do the bootstrap, but I'm going to do the bootstrap 10,000 times. Alternatively, I could now call this function here 10,000 times. So the second alternative is me running 10,000 experiments with 10,000 points in each experiment. So this would actually be you going to the physics advisory committee of CERN and ask them to redo an experiment, which lasted half a year, many more times. The other alternative is to perform the bootstrap, where you reshuffle the numbers with the replacement. So if you now look at the calculations here, if we now just run this code here, what you will see is the following. So you don't get exactly 100. And this is simply because your random number generator is not exactly a stochastic random number generator, and I have only 10,000 points. So this is my first, the original one. So instead of 100, I'm getting something close. I fix these numbers, 115, when I call the function, but when I calculate the mean value, I'm calculating the mean of a sample. And it doesn't give me exactly 100. This is one thing we have to live with. Then, when I now do this resampling 10,000 times, you see now that this goes from 15 divided by the square root of 10,000, which is 100, and you see that's reduced by 100. So what happens then is that my previous distribution had a mean value, which was 100. You see it's a little bit shifted. It should have been here, but it is switched a little bit. So I'm just counting here the histograms, how many times it appears. And what you see now, instead of a spread of 15, my spread is now 0.14. And you see that from the figure here, because I have a mean value getting close to 100, not exactly 100, but then I'm getting into a spread which is much, much smaller. So my standard deviation here, which covers, if you take the mean value, 67% to the left and to the right, is only given by 0.15. So it still looks like a Gaussian. Now, one thing I can do now is obviously to increase the number of points. So let's do that. And then we have to wait a little bit, because this is going to take time. So you will see that this will take more time. But what you will see when I have 100,000 points is that my mean value, mu, for one experiment is getting closer to 100. And my value of 15, the standard deviation, the original one, the original data, is going to get closer to 15. And you will also see that my distribution of mean values, because that's the one I'm sampling over now, or resampling, is going to be much, much closer to the exact result of 100. So let's just wait, and you see now why you want to do resampling, because even now with running with 100,000 points, this is going to take a lot of time. So the resampling is a way to save CPU cycles. So this is still running. And probably it will take a little bit more time, but I suggest we stop here now. And then as soon as this is run, I will put that one into the video here. But this will take a little bit more time. Here we are. Now you will see that it looks much better. I actually should have taken it more up here, but you see now that my standard deviation here, because I had 100,000 points. So now the square root of 100,000 points, and the spread is much, much smaller. Still, my mean value is not the very best one. But this is essentially a demonstration of the central limit theorem using the bootstrap method. The alternative is to simply run 100,000 new experiments. And if your distribution is a complicated mathematical function, then bootstrap is much cheaper from a computational point of view. And that's why the bootstrap method is so popular in statistical resampling analysis. Okay, let's stop here now.